Yeah, we can hear you, Jonathan.
Okay, sorry about the delay there. Yeah, so I'll go through these slides as quickly as possible. I inherited them off Craig this morning. Unfortunately, Craig couldn't be here this afternoon. So first of all, just a very brief introduction to the NAG Numerical Algorithms Group. So when the company started, most of our products are numerical libraries, and so if you may be familiar with NAG through the numerical libraries, NAG numerical libraries and the compiler. But over the years, we've also moved into a lot of consultancy work and into various HPC projects. And our users in consultancy are typically academics, oil and gas, and finance. The libraries probably aren't that interesting to you, but we do have a lot of experience in developing algorithms. And well, there's a list of all the different toolboxes that we have in our library. Probably the more interesting thing is one of the projects we're collaborating at the moment, which is the POP Centre of Excellence, which is funded by the EU. And POP stands for Performance Optimization and Productivity. And we provide various free services to EU organisations. And we also try and promote best practices in parallel programming. So within the consortium, there's a wide range of partners. There's some supercomputer centres in Germany. There's IT4I in the Czech Republic. A couple of organisations in France and the Barcelona Supercomputer Centre. So we've got a very wide range of experience and skills in performance tools, in analysing performance of parallel software and improving performance of parallel software. And as I'm sure you don't need to be told, HPC machines and code is getting more and more complex. And because of this, we've got some funding from the EU to help code developers try to understand the bottlenecks in their code. So there's two main free services that we provide, and you're encouraged to apply for these if they're going to be useful to you. One of them is where we actually analyze the performance of software for some test computations, and we can run the software on customers' hardware or on various supercomputers we have access to. And if you apply for this service, we'll analyze the performance and write a report to try and identify any bottlenecks we find, and typically we spend 1 to 3 months doing this work. And then there's another follow-up service that we offer that some people find quite useful, where we actually work on the code itself and modify the code to try and demonstrate the actual performance that you'll get by taking on board the recommendations we make in the performance assessment. So yeah, so the performance assessment, it doesn't just assess the performance, we try and make concrete recommendations on how to fix it and to find. And the proof of concept work is typically 3 to 6 months of time. One of the key component of the POP methodology is the POP metrics. When we do an assessment, we generate trace data, and I don't know if you've tried analysing trace data, but my experience is often very, very complex and difficult to understand. So we've got this methodology where we generate a hierarchy of metrics to try and help identify the bottlenecks. On the right-hand side, you can see the POP metrics for MPI code. At the top, we have a global efficiency, and then we split that into computational efficiency, where we look at the total time in computation and how that scales. And the other component of global efficiency is parallel efficiency, which tries to characterize the parallelization. And then we split the parallel efficiency into a load balance efficiency and an MPI communication efficiency, and the MPI communication efficiency into a transfer efficiency, which measures the cost of the data transfer, and a serialization efficiency. And we've modified this hierarchy of metrics for MP code, hybrid, MPI open MP code. We're looking at file IO metrics at the moment. So we try and come up with a set of useful metrics to characterize the performance of the code, and then we start to use these metrics then to try and make sense of the trace data. I won't go into the details of these metrics, but yeah, if you apply for this from one of our services, these are the metrics we'll be using. So this is Typically what you end up with for MPI codes, you end up with a table of metrics. This data will have been generated on 2, 4, 8, and 16 compute nodes. And we can see in this code that the global efficiency is 0.59, which tells us that roughly 40% of the runtime is spent in inefficiencies. And by looking down the set of metrics, we can immediately see that the computational efficiency is the key problem with this code. The parallel efficiency is quite high, load balance quite good, and the communication efficiency is quite good. We're only losing a few percent of the runtime due to load balance and communication. And then we can analyze the computational efficiency, look at the instruction scaling and the instruction per cycle scaling to try and get a better sense of what the underlying problems are. And we can see in this code that as we go from 2 to 16 compute nodes, the number of instructions is increasing slightly and the instruction per cycle rate is dropping. And yeah, Craig put together some of the materials codes, or what we understand in materials codes. We're not experts in materials, obviously, we're experts in algorithms and HPC and performance analysis. But these are some of the codes we've been looking at in this phase project, which is phase 2. There was phase 1 that ran a few years ago. And these are the codes that NAG have looked at. So we are looking at quite a few materials codes. So CASTEP, this will be familiar to all of you. I assume that these codes are well known, but I could be completely wrong. One of my colleagues is looking at Turtle at the moment. There's a code called GPOR, which a colleague has just finished analyzing. This is a code which has got, I think it's written in C or Fortran, but then there's a Python layer written on the top, so where we can use the tools to analyze Python code as well as Fortran and C code, as long as it's using MPI. There's another commercial code under NDA that that's been analysed recently. And here's typical kind of results we get. There's proof of concept work in this example at the top, where the runtime was reduced to 72%, and this code was run on Archer. So it was estimated that we're saving just over 15 euros per run, with yearly savings of around 56,000 euros from monthly usage data. Another code that we did a performance assessment on, the client actually implemented recommendations and estimated that they'd improved their operating costs by 20,000 euros. So some of the speed ups people get from applying for a POP service are quite significant. So if you're interested in applying for one of these services, then the best place to go to is the POP website. It's very quick to apply. It's a very simple application form that you can fill in. There's also lots of information on the POP website, blogs, there's a newsletter which you can subscribe to, and there's a webinar series that is fairly popular. We've got a YouTube channel where you can go and see the previous recordings of webinars, which tell you things like how to adopt the POP methodology for yourselves. And yeah, so if you are thinking of applying for a POP service, and we'd love it if people did apply. We've got quite a lot of work on at the moment, but we're always looking for new codes to analyze and to new clients to help. So the project runs until November 2021, so it's probably, if you are thinking of applying for POP, it'd be wise to apply in the next year or so. And I think that's it, really.
Okay, thank you, Jonathan. That's a very nice overview of what you're doing at NAG. Again, if there's any questions, can we feed them through